Good morning to everyone. My name is Ramakrishna, lecturer in physics. Today I am discussing about electromagnetic induction. Okay. So now, what is the electromagnetic induction? Before discussing about this chapter, first of all we have to know the moving charges magnetism. In that moving charges and magnetism, this is one conductor. It carries the current I. When a magnetic needle is placed near to the current carrying conductor, then the magnetic field lines are produced. Here, the magnetic field lines are concentric circles. Okay. It is the current carrying conductor. These are the magnetic field lines. Okay. That means the electric current produces the magnetic field. Current produces the magnetic field. If converse is also possible, that means magnetic field is also produce the electric current. Is it possible? This condition is possible by Faraday experiments. What are the Faraday experiments? Faraday experiments. For example, here you can take one circular coil. It is connected to the one galvanometer. Galvanometer shows the amount of current is flowing in the coil, and you can measure the small amount of currents. Now you can take one bar magnet, that is, this is north pole and south pole. When the magnet is at rest, that is its velocity equal to 0, then whatever the magnetic field lines are coming from the ball magnet, those are linked with the coil. Now the magnetic field lines are not, the magnetic field linked with the coil does not change. Okay, so there is no current produced in the coil. Deflection in the coil is deflection is equal to 0. But you can take one coil. This is galvanometer. Now this is one bar magnet, north pole or south pole. If it is moving in this direction, then what happens? The magnetic field will be increases, which is linked with the coil. When the magnetic field changes, the magnetic flux also changes. Okay. Due to that change in magnetic flux, some current is induced in the coil. Due to that current, the galvanometer shows the deflection. Similarly, if the coil is moving away from the if the magnet is moving away from the coil, then the flux linked with the coil is decreases. Due to that, the current in the coil is also decreases. Due to that decreasing current, the galvanometer shows the deflection in opposite direction, that is in right side. Similarly, when the poles of the magnet changes, when the bar magnet, that is south pole of the bar magnet, is moving towards the coil, then the galvanometer shows the deflection on right side. When the south pole of the bar magnet is moving away from the coil, then the deflection in the galvanometer shows the right side. From this Faraday first experiment, what we conclude, whenever there is a relative motion between the coil and the magnet, some current is induced in the closed coil. Okay, that phenomenon is nothing but electromagnetic induction. And another experiment is there. Instead of bar magnet, can take another coil, that is, this is first coil. Galvanometer, and this is coil C1. This is connected to one battery. Due to that battery, it is positive, negative. The current is flowing from positive terminal to negative terminal. Okay. Here, what is the direction of current in the coil? This is the clockwise or anti-clockwise? Clockwise currents. Clockwise direction. Due to that clockwise, the direction magnetic field is in this direction. When the coil is moving towards the C1, then what happens? The magnetic field linked with the C1 increases. Due to the increase in magnetic flux, the current in the C1 induced. Due to the induced current, the galvanometer shows the deflection, that is in this direction. When this C2 is moving away from the C1, the galvanometer shows deflection in opposite side. Then from this second experiment, how can explain or how can conclude? Whenever there is a relative motion between the coils, then current in the coil is induced. The current is induced in the coil. Now, from these two experiments, how you can give the definition of electromagnetic induction? That is the phenomenon of electric currents induced in the closed coil by varying the magnetic fields is called the electromagnetic induction. In this chapter, we have to discuss about magnetic flux. What is the magnetic flux? Okay. Magnetic flux. It is indicated by the letter phi. How can I explain the electric flux in electrostatics? In the same way, magnetic flux also explained. The total number of magnetic field lines passing through any surface in a direction normal to the surface. That is the total number of magnetic field lines are passing in a direction normal to the surface is called magnetic flux phi. Okay, that is called the magnetic flux. For example, I can take one small surface, imaginary surface. In that surface, can consider one small area, that is A. Now, what is the area vector or normal vector or unit vector? It is always perpendicular to the surface area. Now, this surface is placed in the magnetic field, which makes angle theta with the normal. Now, B can be resolved to two components. This is the B sin theta and this is the B cos theta. What is the flux? Flux is nothing but this is the product of component of magnetic field in a direction normal to the surface, normal to the plane of the surface. That is called the magnetic flux. That is B cos theta into A. That is flux phi equal to BA cos theta. That is BA cos theta. And what is SI unit? SI unit Weber. CGS unit Maxwell's. One Weber equal to 10 power 8 Maxwell's. 1 Weber equal to 1 Tesla meter square. 1 Tesla meter square. Flux is a scalar quantity. Flux is a scalar. Flux may be positive or negative or zero. Okay. Understand? When the flux is positive or negative or zero, Example, this is one surface, this is a cylindrical surface. This is the direction of magnetic field. Here you can imagine three surfaces or three plane of surfaces. This is first surface and it is second surface. This is the third surface, and it is also fourth surface, four plane of surfaces. If you take this first region, what is the unit vector or normal vector? Unit vector or area vector is always perpendicular to the surface. Here unit vector, this is the n cap and this is the n cap and it is the n cap. Okay. For first region తీసుకున్నట్లయితే, here the plane of the surface is parallel to the magnetic field B. Plane of surface is parallel to B, or n cap is perpendicular to B bar. That implies, what is the angle between these two? 90 degrees. This theta equal to 90 degrees. Therefore, what is the flux? Phi equal to BA cos 90, that is equal to 0. Therefore, flux phi equal to 0. Second region. What is the second region? Here n cap is anti-perpendicular. N cap is anti-parallel to B bar. That is, B bar is in this direction. B bar, this is the direction B bar, but n cap, this is the direction. What is the angle between these two? 180 degrees. That is, theta equal to 180 degrees. Flux phi equal to BA cos 180, that is equal to minus BA. Therefore, flux phi equal to minus BA. Next, for third region, what is the unit vector? This is the direction of n cap. P bar is also same direction. What is the angle? This into theta equal to 0 degree. Flux phi equal to BA cos 0, that is equal to B into A అవుతుంది. That implies flux equal to BA. It is positive or negative? Positive. Here negative. It is phi equal to 0. Flux may be positive, negative or 0. Okay. Now have to discuss about what is the magnetic flux associated with the coil. magnetic flux associated with a coil. Okay, for example, this is one coil having n turns. Area of cross section of the coil is A. Here, this is the direction of unit vector or area vector. Now, this is the direction of magnetic field. Sorry, general formula. First of all, you can take a general formula. Area. Let us consider a coil having n turns and the area of cross section is capital A. Now, this is the direction of unit vector. Now, if the coil is placed in a magnetic field, uniform magnetic field, which makes angle theta with the unit vector or normal vector, then what is the flux? Flux phi equal to NBA cos theta. NBA cos theta. Here, the flux may be changed by changing the number of turns in the coil, by changing the magnetic field in the coil, by changing the area of the coil, and flux may be changes by orientation of the coil. Orientation is nothing but rotation of the coil. Okay? Now, for example, this is the coil and it is the direction of normal vector, unit vector. The magnetic field is parallel to the plane of the surface. Parallel to the plane of the surface. Then flux, here what is the angle? 90 degrees. Flux phi equal to 0. Flux phi equal to, sorry, cos 90 equal to 0. Yes, sir. If this is the coil, this is the normal vector, and this is the direction of magnetic field. Magnetic field. Then what is the unit vector? This is the n cap and it is the b bar. These both are in the same direction. Theta equal to 0 degree. Theta equal to 0. Therefore, flux phi equal to NBA. Flux phi equal to NBA. This is the coil and normal vector. This is the opposite direction of magnetic field B. That is theta equal to, what is the angle? N cap upward, B cap, B bar downward. Theta equal to 180 degrees. Theta equal to 180 degrees. That is flux phi equal to minus NBA. Minus NBA. Okay, this is the flux linked with the coil. Whenever the magnetic field makes some angle with the normal, then flux phi equal to NBA cos theta. If the magnetic field is along the plane of the coil, then flux phi equal to 0. If the magnetic field is perpendicular to the plane of the surface, flux phi equal to NBA. if the magnetic field is in a direction opposite to the normal vector, then B equal to flux phi equal to minus NBA. Okay, understand? Magnetic flux due to orientation of the coil. Magnetic flux due to orientation of the coil. For example, here a coil has a N turns and area of cross section A is rotated from theta 1 to theta 2. Theta 1 to theta 2. Then what is the flux? Initial flux phi 1 equal to NBA cos theta 1. Final flux phi 2 equal to NBA cos theta 2. What is the change in flux? Change in flux is delta phi equal to phi 2 minus phi 1. That is delta phi equal to phi 2 is nothing but NBA cos theta 2 minus NBA cos theta 1. That is delta phi equal to NBA, we can get a common, that is cos theta 2 minus cos theta 1. This is the change in magnetic flux. Change in magnetic flux. Change in magnetic flux. If theta 1 is equal to 0 degree and theta 2 equal to 90 degree, what is change in flux? Delta phi equal to cos 90 equal to 0, cos 0 equal to 1, that is minus NBA. If theta 1 equal to 90 degrees, if the coil is rotating from 90 degrees to 180 degrees, that is delta phi equal to cos theta 1 equal to 90, 0, cos 180 equal to minus cos 90, 0 minus NBA. If theta 1 is equal to 0 to theta 2 equal to 180 degrees, then what is the change in magnetic flux? Delta phi equal to cos theta 2 minus 1. Here cos 0 1 minus 1 minus 1 minus 2, that is minus 2 NBA. Okay, based on this magnetic flux we can discuss some problems in next class. Thank you.